Welcome back. So, after the last 3 lectures, neural networks, reinforcement learning in continuous spaces, and neural Q-learning and neural SARSA, we are ready for a Matlab example. So, with neural Q-learning, if you recall the previous video, I will go a little bit fast because if you want to learn more a slow down pace version, watch the video called Neural Q-learning and SARSA. We initialize theta values in Q-learning, take an action, it can be random with some probability, apply action, measure the next state, get reward, and use all of them in the update rule to update theta, and then until convergence or the end of episodes, repeat from step 2. And once you repeat, everything is nice and converge. When they converge theta values, get the optimal policy pi star like this. All right, so here is a Matlab example. I choose gamma, alpha, epsilon like this. It is for the example that we used before. You have 3 states. Right, state 1, 2, and 3. Action can be -1, meaning go left, or if it is 1, go right. We would like to reach the terminal state, and terminal state is located at 3. So, right by observation, your optimal action should be right, and you are done with the game. And when you are at the terminal, when you are at the second state and decide to move right, then since this will make you reach to the terminal state, you get a reward, 5 points. All right, so I choose, this is the width for the radial basis function. By the way, here I should mention, I am using the radial basis function like this. Instead of having D1 and D2, I have the center and sigma. Because I adopted this from one of my other codes here. Instead of using the notation X and A, I am using X and U because in control theory, if you have background, X represents the state and U represents the action. Reinforcement, I switch for these videos S to A because reinforcement learning people like those S and A. So if you saw X, interpret this as S. If you saw U, interpret as A. Okay. As this being said, I choose 1, 2, 3, 4, 5, 6, 7, 8 neurons. And since we do this action separation, total features are separated. So this f of x includes the bias and 8 radial basis functions. But since we have left and right, we have a set for action left, a set for right. You can watch to the end of the previous video on this playlist. We discussed this action separation so that each action is well represented within our radial basis function neural network basis. And initializing the weights, as you see here, I choose a random. It is a small random initialization. If you don't like it, you can consider it to be 0. Here is the reward. I am recording theta history. This is for recording purposes. Radial basis function here, the feature vector is the basis function that, it uses this Kronecker product, and this rep math, it chooses the set specific to some action. If you are using left, you'd consider this set, otherwise consider other set. All right, here is the iteration loop. It is not much different than the Q-learning example we did a couple videos back. The only major difference, I guess, is we are not using Q-table, but we are using basically, this is our basis transpose multiplied by the theta. Again, S is X, U is action. This is the same if you're on state 1, go to, and if you get -1 left, you cannot go to 0, so stay there. And if you are state 1 and make is control is 1, then go to state 2, this transition stuff. After that, you observe the reward, and then this peak current, and we write to compute the Q value for the current state action pair, basically T prime multiplied transpose multiplied by theta. Then we estimate Q value for the next state like this, getting this max phi transpose theta A prime business here going on. And then we compute this Q0, if you remember this, the one coming from the Bellman. Basically, it is reward plus gamma Q max next. Q max next was here, we are using here. Then this we write this error, Q target minus Q current, and final theta is alpha delta multiplied by phi current. So I represent it here. If you take and put it back, and if you watch a little bit, it is nothing but I just computed this, but element by element, Q target minus Q current multiplied by phi, basically, right? Q target minus Q current multiplied by phi current. All right, recording the theta history and for visualization, and this is the extracting the optimal policy and then displaying some figures, which are these. So as you see, basically we run, and this is how the weights theta associated with, we had 8 neurons plus bias 9 for left action, 9 for right action. So basically we have 18 parameters estimated here. Basically I stopped here, but if you go, the reason I stopped, it is converging around 400 iterations. If you go more, it is more or less like this. And when I extract optimal policy, if you're on state 1, move right. If you are at state 2, move right, so that you're at the terminal state. That's awesome. So we nicely approximate. Of course, this is a simple example, but the reason I choose a simple example so that I can share with you the entire code, and it is easier to understand. And of course, when you can take a homework if you wish, do it for two-dimensional example with states on the X changing from 1 to 10, on Y 1 to 10. It will be, you need to code it yourself. So that's why I'm not providing directly the code, but you can take screenshots and then you code it yourself. This is a really important experience, and you should try such homeworks like 2D examples. And you can leave a comment, and I will try to help. All right, so let's do the example with the neural SARSA algorithm. I explained here you have your current state. You have your current state S. You take an action A, then you get reward and the next state S prime, and you take action again, SARSA, state action, reward, state action. And then when you take the action after you receive S prime, you again, with some probability, you take optimal action, A prime next action, or it can be random with some probability, and you update theta, but now you are using S prime and your actually A prime that you just take. So you are learning from the experience from your actions. And then you repeat step 2 until converge. Again, I went fast in this part because really I explained this in the previous video on this playlist. You can go and watch. And finally, you extract optimal policy like this. All right, so it's called going like this. I'm not going to repeat the similar steps. I don't see anything different here, really. Features are defined the same way, basis function defined the same way. Nothing different here. For completeness, I shared the entire code, okay? So this is the SARSA version. Transition here, I guess the only difference is how I calculate the Q target, Q next. Okay, here. First, we took, this is for calculating A prime, and then I am using S prime and A prime, basically X next and U next, to get phi next, and then we basically calculate the target minus Q again. Again, if you go back to here, I'm calculating Q target, what I called in the code, and Q current, and then multiplied by phi, which is done. Theta is theta alpha multiplied by this. All right, and this is a little bit longer, right? Since I need to calculate A prime again, and this is the basically determining the optimal policy and displaying figure and the final results. For this simple yet I hope informative example, for SARSA your weights changing like this, convergence, it is arguable. You can say it is converging around here, but since they are, some of them are a little bit changing here and there, I will say maybe I don't want to give, some, if I talk with some of my colleagues, they may call it is converged here. If I call it with some of the picky ones, they say it is still not converging there, but practically it is converging. I mean, if I stop, and I did stop at 400 iterations or 250 iterations, you still get the same optimal policy, 1-1. If you're on state 1, go right. If you're on state 2, go right. So from this standpoint, it is still great, but this was the example. I hope you like it, you enjoy it. So see you in the next class. Take care.